the orbit that should not be stable. For years, it behaved as if the universe had made a mistake and then refused to correct it, circling in defiance of equations that had predicted its collapse long ago. Every calculation said it should have fallen apart, drifted away, or been torn free, yet remained exactly where it was, quietly challenging everything astronomers thought they understood. To understand why this orbit still matters today, we need to revisit how stability is defined in space. Orbital mechanics are built on rules refined through centuries of observation, rules that allow scientists to predict motion with extraordinary accuracy across immense distances and timescales. Modern navigation, satellite systems, and deep space missions all depend on the assumption that these rules are reliable, because even small deviations can cascade into failure. That reliability is what made this discovery so unsettling. The orbit was first flagged during routine analysis, buried deep within datasets that were never meant to reveal surprises. At a glance, it appeared unremarkable, just another object following a predictable path around a much larger body. But when researchers extended their models forward and backward in time, the math began to unravel. According to every known influence, the orbit should have destabilized thousands, perhaps millions of years ago, yet the object was still there. As simulations grew more sophisticated, the contradiction sharpened. Adding more precision did not resolve the problem. It amplified it. The orbit was not marginally stable or temporarily balanced. It was persistently stable in a configuration that theory insisted should not survive. The universe was not merely bending expectations. It was holding them in suspension. What made this moment profound was not the anomaly itself, but what it implied. If one orbit could defy prediction so completely, then the certainty surrounding countless others began to feel less secure. The question was no longer how this orbit existed, but how many assumptions had quietly gone unchallenged simply because they had never been tested this way. As attention focused on the anomaly, researchers began dismantling their own assumptions piece by piece, because the stability of the orbit could not be dismissed as coincidence or error. Every known gravitational influence was accounted for, from nearby bodies to distant tidal effects. Yet the calculations stubbornly returned the same result, that the orbit should have unraveled long before any observer could have witnessed it. What complicated the investigation was how ordinary the system appeared at first glance. There were no extreme masses, no chaotic interactions, and no obvious external forces acting to preserve balance. The environment matched countless others that behaved exactly as predicted, making this exception feel deeply uncomfortable rather than exciting. The universe was following its rules everywhere else, just not here. As models were refined, attention turned toward interactions that were usually negligible, subtle resonances, long-term feedback loops, and minute energy exchanges that accumulate over immense timescales. Individually, these effects seemed too weak to matter, but together they began to suggest a fragile architecture of balance that had been overlooked because it rarely revealed itself so clearly. Debate intensified as interpretations diverged. Some argued the orbit represented a rare but natural configuration, one that existed within the margins of existing theory, but had simply never been observed directly. Others believed it pointed to missing components in the models themselves, influences that had been smoothed away in pursuit of simplicity and efficiency. The deeper the analysis went, the more unsettling the implications became. If stability could emerge from interactions previously considered insignificant, then the boundary between predictable and unpredictable motion was thinner than assumed. Systems thought to be well understood might harbor hidden modes of behavior, waiting only for the right conditions to appear. In that uncertainty, the orbit transformed from a curiosity into a challenge, not observation alone, but to the confidence with which humanity claimed to understand the mechanics governing the cosmos. The conflict reached its most intense phase when attempts to explain the orbit began to undermine principles that had anchored orbital theory for generations, because preserving the anomaly required accepting interactions that models were never designed to prioritize. The equations still worked in isolation, but when applied to the system, they revealed a fragility beneath their apparent certainty, exposing how much stability depended on assumptions rather than guarantees. As teams ran increasingly complex simulations, new behaviors emerged that felt almost counterintuitive. Minute gravitational nudges, once dismissed as background effects, began to synchronize over long periods, reinforcing rather than disrupting the orbit. Instead of chaos accumulating into collapse, order emerged from repetition, suggesting that stability could arise not from dominance, but from balance maintained through constant adjustment. This realization created tension within the field. Accepting the explanation meant acknowledging that many orbital systems might exist in states far more delicate and dynamic than previously believed, balanced on interactions, so subtle they escaped detection until extreme precision made them visible. Rejecting it meant accepting that something fundamental was missing from current understanding, an option that carried even greater uncertainty. What made the moment uncomfortable was how little drama accompanied it. There was no singular breakthrough, no equation rewritten overnight, only a gradual erosion of confidence in the idea that stability is simple to define. The orbit did not defy physics outright. It exposed how narrowly physics had been applied. As discussions deepened, the anomaly became a mirror reflecting a broader challenge in science. Models are built to explain the common case, not the exception, yet it is often the exception that reveals where understanding ends. This orbit existed not at the edge of chaos, but at the edge of certainty, forcing researchers to confront the limits of prediction itself. The question now was not whether the orbit could be explained, but whether doing so would require redefining what stability truly means in a universe governed by interactions too subtle to ignore. The climax of the story arrived when the anomaly was no longer treated as an exception to be resolved, but as evidence that stability in the universe is far more nuanced than once believed, because the orbit did not survive by resisting change, but by continuously adapting to it. What appeared impossible under simplified assumptions became inevitable once long-term interactions were allowed to matter. The resolution reshaped more than a single model. Researchers began revisiting other systems once considered settled, re-examining them with an awareness that hidden balances might exist beneath apparent simplicity. Stability was no longer defined as rigidity, but as resilience, the ability of a system to absorb influence without losing coherence over time. This shift carried broader implications. Spacecraft navigation, planetary formation theories, and long-term predictions all rely on assumptions about how systems behave under stress. Recognizing that stability can emerge from complexity rather than clarity forced a reevaluation of how certainty is claimed in environments governed by countless interacting forces. Today, the orbit remains where it always was, unchanged by the debate it inspired, continuing its quiet defiance of outdated expectations. It does not announce its lesson loudly, but offers it patiently, that the universe often sustains order not through simplicity, but through relationships too subtle to notice until they are questioned. Sometimes discovery does not come from finding something new, but from realizing that what we thought was fragile has been stable all along, for reasons we are only beginning to understand. Subscribe to join the journey. The